Right, we are focusing on these exercises and we want to find the point of discontinuity of the following functions. A f of z equals 2z minus 3 all over z squared plus 2z plus 2. B f of z is the cotangent of z. C f of z is 1 over z minus the secant of z. D is f of z equals the tangent of z. E f of z is the hyperbolic tangent of z divided by z squared plus 1. And we are going to proceed to write the solution to the set of exercises or the solutions to all these. But also, if you need any assistance, you can WhatsApp us on +27 82 044 8712, and we can assist you with more problems in mathematics and science. Okay, so we proceed to find the points of discontinuity of the functions. All right, now we focus on 1a next. Right, so we have f of z equals twice z minus 3 all divided by z squared plus 2. And now we proceed to let. Right, we let z squared plus twice z squared plus twice z plus 2 be equal to 0. This means minus b plus or minus the square root like this of b squared minus 4ac all over twice a, and this is minus b, which is minus 2 plus or minus the square root of b squared, which is 2 squared minus 4a is 1. Right, so a is 1. C is 2 divided by twice a, which is 1. So this is minus 2 plus or minus the square root of. Okay, so this is exactly the same as 2 squared, which is 4 minus 8 divided by 2, all divided by 2 by 1, which is exactly 2. Right, which is minus 2 plus or minus the square root of 4 minus 8 is exactly minus 4, all divided by the square root of. Okay. Now, this is minus 2 plus or minus 2i divided by 2. All right. And if you divide, this is minus 1 plus or minus I. Right. Hence the points of discontinuity. Hence the points of discontinuity are given by z minus 1 plus I. The other one is z equals minus 1 minus I, like this. Okay, so there are two of them, and the okay are these two values of z. Okay, next we proceed to do the next one. The next one is problem 1b, and 1b is f of z equals cot of cotangent of z. Right, so we focus now on 1b, and this is f of z equals cotangent of z. But cotangent of z is the same as cosine z divided by, okay, so proceed now. Need to clean this up. Need to clean this up. Okay, just a sec. Need to clean this up. Right, so we proceed to solve this and we say the cotangent is the same as cosine z divided by the sine of z. Okay? And then now, for point of discontinuity, we let the sine of z be equal to 0. Okay, so yeah, just a sec. We clean this up. So we have the sine of z be equal to 0, like so. And we know very well that this actually implies that e to the I z minus e to the minus I z all divided by 2I equals 0. Cross multiplying everything means Iz minus e to the minus Iz equals 0. Multiplying both left and right by e to the Iz means e to the Iz squared is 1. Right. And this is the same as 2Iz. Goodness me. Is the lean natural log of 1. But the natural log of 1 is 1e, right at the bottom. But the natural log of 1 is the same as what? So in other words, we can solve for that here. And you have 1 divided by twice I. Right, the natural log of 1 is the natural log of 1 times e to the I into the argument of 1, which is 0 plus 2 pi k, like so. So we have this. So every complex number can be written in this form. Right. And obviously understand that k is an element of the set of integers here. And what is all this? And this means that z is exactly the same as what? Right. So the 1 over I can be seen as minus I out of 2 into the natural log of 1 plus I 2 pi k. K is an element of the set of integers, like this. Okay. But now ln 1 is actually the same as 0, at least on the reals. So we proceed to simplify these. So that is minus I out of 2 into the ln of 1 plus I 2 pi k, k in z. All right. Right, so this is the same as what? Right, so the ln of 1 is 0, giving us I, 2 pi k, k in the integers. And if you multiply 2 cancels and I, so you have I minus I and I give us 1. So you have this. Hence, the geometric sign of Z equal to 0 implies that Z equals pi k, where k is an element of the set of integers, like this. And therefore we are done. So now the question becomes that that's the points. That's the points. The points of discontinuity of f of z equals the cotangent of z occur, right? So occur at z equals pi k, where k is an element of the set of integers, like this. Okay, so yeah, we're done with this one. And we proceed to look at 1c. 1c, right? So if you look at 1c, what do we have in 1c? Right, we have f of z is the same as 1 over z minus the secant of z. 1 over z minus 1 over the secant is the cosine of z, which is cosine z minus z divided by z cosine z. So what we do, we let z cosine z be 0 for the points of discontinuity. And this means z is 0 or cosine z is 0. Right, so if we have that z is 0, or if cosine z is 0, it means e to the I z plus e to the minus I z all divided by 2 is 0. E to the I z plus 1 equals 0. E to the 2iz, like this. Okay, so now you can take the natural log on both sides, meaning 2iz is the natural log of minus 1. Right, so this is what we get. 2iz is the natural log of minus 1. So if we have the 2iz, is the natural log of minus 1, but the natural log of minus 1 is the natural log of 1 times e to the I. The argument of minus 1 is pi plus 2 pi k, k in the integers. K is an element of the set of integers, so this one is 1 plus I pi plus 2 pi k, like this, k in z. So you have 2iz. Right, so now this means 2iz is the natural log of 1, 0. And then we have I into pi plus 2 pi k k an element of the set of integers, meaning z is I divided by 2I into pi plus 2 pi k, where k is an element of the set of integers. So yeah, so obviously I cancels out, and we can pull out I as a pi as a common factor. This gives us pi over 2 into 1 plus 2k, where k is an element of z. Okay. Hence, the singular, or rather the points of discontinuity, which are the singular points. Just use the points of discontinuity. Hence, the points of discontinuity hence the point of discontinuity of f of z. 1 over z minus the secant occur, they actually occur at z equals pi out of 2 into 1 plus 2k, where k is an element of z. Okay, yeah, but this is a possible way to do the problem, but there's a shortcut. So from here, somebody can look at this and think, okay, this automatically implies that we know that the cosine is 0 at pi over 2, 3 pi over 2. So it is 0 at pi over 2 times the odd multiples of pi over 2, sorry, which is 1 plus 2k, where k is an element of z. So it's something that obviously you can be aware of there. So yeah, just take note of that. The next one we do is, so in other words, this is 1c we're doing. And obviously this one is a continuation of the problem 1c, like this. Right, we continue to solve more problems, and now we look at question 1d. Question 1d. So here we have f of z equals the tangent of z. So this is the trigonometric sine of z over cosine z. Okay. So what is this? Right, we've already seen, sorry, from the previous question, sorry, we let cosine z be equal to 0. Okay, so let's clean this up. Let's just clean this up here. Right, so we let the denominator be 0 for the point of discontinuity. So we let cosine z to be 0. And if it happens that cosine z equals 0, we already know that this implies that z is actually the odd multiples of pi over 2. So it is pi over 2 into 2k, where k is an element of z, like this. So this is what we get as the solutions to this problem. So which means z is pi over 2 into 1 plus 2k, where k is an element of z. And hence, We solved the cosine z equals 0 equation from the in the previous question in detail. Hence the points. The points of discontinuity. Right, hence the point of discontinuity of f of z cos 10z occur at z equals pi over 2 into 1 plus 2k. K an element of z. Right, k an element of z. So just a minute, let me clean this up. Right, so k an element of z, and we have this here. So k an element of z. Hence, the points of discontinuity or of f of z equals the 10 of z, or k at z equals pi over 2 into 1 plus 2k, where k is an element of z. Okay, we're just to find the points of discontinuity there. Okay, next we focus on the next question. And the next question is 1e. As you saw in the beginning, in 1e is as follows. Right, next we focus on 1e. What is 1e? Is f of z is equal to the hyperbolic tangent of z divided by z squared plus 1, like this. But the hyperbolic tangent is the same as the hyperbolic sine of z divided by cos of z divided by z squared plus 1. Hyperbolic sine of z divided by z squared plus 1 cos of z. Right, at this point, we let the denominator be 0 for the point of discontinuity. So we let z squared plus 1 into the cos of z to be equal to 0. And this means that z squared plus 1 is 0, or the cos of z is 0, which means that at this point we have z squared is equal to minus 1. Right, the cos is the same as e to the z plus e to the minus z out of 2 is 0. Upon further examination, this is plus or minus I, like this. Okay, so you cross multiply here and convert this, so this becomes e to the 2z plus 1 is 0, which means e to the 2z is equal to minus 1, which means therefore that 2z is the natural log of minus 1. Okay, we can see that this is the case. Now let's proceed to solve this problem in detail. So we have 2z is the ln of minus 1. 2z is the ln of minus 1, which is the ln of 1. Okay, so this one becomes the ln of 1, and then if it becomes then the ln of 1, you put the argument, which is pi plus 2 pi k, k in z, plus I pi plus 2 pi k. k in z. So this is 2z. 2z. The ln. So we have pi plus 2 pi k. K in z. Right, so we divide by 2. So pi plus 2 pi k. Okay, like this. Which means you can pull out the pi, which is a common factor, giving us pi I out of 2 into 1 plus 2k, where k is an element of z. Right, hence the points of discontinuity of the function f of z equals the hyperbolic tan of z divided by z squared plus 1 or k at, we saw that z is plus or minus I, or z is pi I out of 2 into 1 plus 2k k in z. Like this. Okay. Right, we're done with that one, and we proceed to look at more problems. So the next question is as follows. Is number 2. And number 2 says you need to show that. We need to show that f of z equals 2z cubed minus z plus 3 is continuous. Everywhere. Is continuous everywhere in the finite plane. So we solve this one. In the finite plane. Okay. So there are a couple of things that we need to consider for that. Sorry, to solve this problem. So we look at the solution to this one. And what is the solution to this? Right, the solution is as follows. So we shall let Z0 be an arbitrary complex number in the finite plane. In the finite plane. Right. So we proceed like this. So there are a couple of things that we need to look at. The first thing here is to say f of z0. We plug it into this equation, which is 2z0 minus z0 plus 3. Okay, sorry. This one is defined. Oops. Right, so we write like this and realize that this is defined. So f of z is defined. Right, point 2 is we find the limit as z approaches z0 of f of z. What is the limit of this function? So with the limit as z approaches z0, and this is 2z0 cubed minus z0 plus 3. Okay, first we put the function as it is without the zeros here. Okay, so we have that. So this is plus 3, and if we take the limit, this is 2z0 cubed minus z0 plus 3. So this limit exists. Right, so the third point is to say the limit as z approaches z0 of f of z is f of z0. Okay, once we can say these particular three things, that these things are true, the conclusion therefore is that hence since z0 was arbitrary, it follows that f of z, which is 2z cubed minus z plus 3, is continuous everywhere in the finite plane. So that is the conclusion. It follows that f of z is continuous everywhere in the finite plane. So right, we look at the next question. And the next question is 3. Question 3. Question 3, we need to show that f of z equals z squared plus 1. Okay, let me reset my device here. Right, so let's just get this device reset properly. Right, we proceed with solving these problems here. Let me clean this up. Right, and we say z squared plus 1 divided by z cubed minus 9. So we need to show that this function is continuous and bounded. So let's just continue. Okay, I'm just cleaning this up. So we need to show that this function is continuous and bounded. Okay, and with that said, is continuous and bounded. and bounded in the region. Mod Z is less or equal to 2. Okay. So now, what do we do? So we clean this up a little bit. Okay, so we're going to look at the solution to this. What is the solution to this? So the solution to this is as follows. The solution to this is, right, first we need to show that it's continuous and bounded in the region that, sorry. First things first, for continuity, we need to take an arbitrary point in the region. So we say let. That means white. Let. Right, do not change the color. Need to change the color. So we let Z0 be an arbitrary complex number. Complex number in the region. Mod Z is less or equal to 2. Like this. Okay. With that said, what do we do? Right, a couple of things that we just need to consider here. And so we can take f of z0, 0.1. F of z0 is z0 squared plus 1 divided by z0 cubed minus 9, like this. Is defined. We claim that it is defined. Right, it is defined. I mean, how is it defined? It is defined where the z cubed minus 9, z0 cubed minus 9 is actually, we can say, if this is 0, if this is equal to 0, what does it mean that this is 0? Right, so if the denominator, if it happens that z0 cubed minus 9 is 0, this means z0 is 9 to the power 1/3. Okay, and now what would this be, for example? In any case, if you take the modulus of this, you can take the modulus or anything like that. So the modulus of this, or you just get an estimate of this, is going to be approximately 2,08808, like this. So that in the end, what we have so that the 2 comma 088 08 is bigger than 2. It is bigger than 2. So in other words, um, this denominator is 0 outside this region. It's so that it's bigger than 2. And since it's bigger than 2, the conclusion is therefore that this is defined in the region. It reinforces that. Thus, f of z0 divided by z0 cubed minus 9 is defined in the region. Okay, what region is this? Right, it's defined in the region. This is modulus of z is less or equal to 2. Okay, can remove the comma here. Like that, sorry, yeah. All right, so now we have proven that it is defined. So the next thing is to find the limit as z approaches z0 of f of z, which is the limit as z approaches z0 of z squared plus 1 divided by z cubed. So if we divide this, what do we get here? Okay, if we compute this, so this is z0 squared plus 1 divided by z0 cubed minus 9. Sorry. Well, the conclusion, therefore, is that this limit in particular, well, it follows also that this limit exists. The third point is that this limit of f of z as z approaches z0, this limit is actually equal to f of z. Clearly, it is equal to f of z. And hence, f of z equal to z squared plus 1 divided by z cubed minus 9 z squared plus 1 over z cubed minus 9 is continuous. Is continuous in the region. It's continuous in the region. Okay, let me just clean up. All right, just clean this up. Just one sec. Just one sec. Right, so it is continuous in the region that is continuous in the region. In the region, modulus of z is less or equal to 2, like this. Okay, there are a couple of things we need to like look into more in more detail, that are important for us. Okay, we need to now look at the boundedness part of it, because if you look at the question, we're supposed to show that this is continuous and bounded. So we have shown that it's continuous, and we need to look at the boundedness of the function. So let's proceed to look at the boundedness of the function. So we look at the boundedness. Boundedness. Right, to focus on the boundedness of the function, a couple of things we need to look at. So we let f of z be z squared divided by z cubed in the region that so that you can take the modulus divided by z cubed minus 9. And this is less or equal to the modulus of z squared plus 1 by using the triangle inequality. Here using the reverse form of the triangle inequality, we have the cube minus, then you take the reverse form of the triangle inequality or the backward form. And this is less or equal to, so this will be 2 squared plus 1. Divide by that denominator, you're going to have 2 cubed minus 9. 5 divided by 8 minus 9. Okay, 8 minus 9 modulus, so it's going to be 5. And this means, therefore, that the modulus of this function is less or equal to 5. Like this. And now, there are a couple of things you need to just to make mention of here. The triangle inequality. So in other words, we can say, hence, right, we draw the conclusion that hence, what do we say? Hence, f is bounded. Can write properly here. Hence, f of z equals z squared plus 1 divided by z cubed minus 9 is bounded. Is bounded since there is a constant. The constant 5 positive, such that is less or equal to 5 for all z in the complex numbers, like this. So, right. So we have proven that it is necessarily bounded since there is a constant such that that is the case for all z in the complex numbers, elements in the complex numbers in the region. In the region, the modulus of z is less or equal to 2. So now there are a couple of things that are important, like when you look at your triangle inequality. Okay, what is the triangle inequality? So the triangle inequality states that if you have complex numbers, z and w, this is going to be less or equal to the modulus of z plus the modulus of w. Z and w are complex numbers, elements of the set of complex numbers. And there's something, therefore, we analyze and we call the reverse triangle inequality. Triangle inequality. Okay, you don't want to call it the reverse triangle inequality. You call it the can call it the backward form. Right, the reverse triangle inequality. Do you want to call this? You call it the backward form. Backward form of the triangle inequality. What is it, this backward form? It says if you have the modulus of z plus w, it is certainly greater or equal to the modulus of z, like this, the modulus of z minus the modulus of w, like this. Okay, this is called the backward form of the triangle inequality. Now, there is another question that we need to do now. And it is this one. Question number 4. We need to show that f of z equals 1 over z is continuous for all z such that it's continuous for all z such that, just clean this up, for all z such that the modulus of z is strictly bigger than 0, but is not bounded. Is not bounded. So look at the solution now. So let's focus on the solution to this. Need to show that it is continuous for all z in that region. Right. So to prove continuity, we begin as follows. So first we look at continuity. Right. So for continuity, we let z0 be a complex number. Let z0 in C be arbitrary. Be arbitrary. The first point is to notice that f of be arbitrary, you can state here with f of z equals 1 over z. So f of z0 is 1 over z0 is defined. F of z0 is defined so obviously, most importantly here, if z0 is there is arbitrary with that is the case, f of z 1 over z and z modulus of z bigger than so is defined with the modulus of z0 strictly bigger than than 0. Well, obviously we know it's defined when z0 is not 0. Z0 is not 0. Okay, so just note that. Let's just clean this up. So you state here that Z0 is not 0, obviously, because the modulus is bigger than 0. The next thing is the limit. The next thing is the limit of f of z as z approaches z0. This limit, 1 over z, and this is 1 over z0. So now this limit exists. With the modulus of z0 being strictly bigger than naught. Thirdly, the limit of f of z as z approaches that. This limit is f of z0. Where the modulus of f is bigger than 0. Hence, f of z equals 1 over z is continuous. For all z such that is bigger than 0. Is continuous for all z such that the modulus of z is strictly bigger than 0. The next thing is to focus on the boundedness part of the 1 over z function. So we look at the boundedness. How do we focus on the boundedness? So to look at the boundedness, we let f of z be 1 over z for all z such that mod z is bigger than 0. Then we can take the modulus of this, which is the modulus of this, right? Which is 1 over, so you can take the modulus of 1 divided by the modulus of z, which is 1 over the modulus of z. Right, so what is 1 over the modulus of z? So 1 over the modulus of z is going to be less than infinity. Right, so this is less than infinity. Right, a couple of ways to look at this and understand it, because if you have then for all z, the modulus is that. So we know that the modulus of z bigger than 0 means you can take the reciprocal here of 1 over the modulus of z, which becomes less than this. And this is 1 over the modulus is less than infinity, like this. So just look at this. Obviously, 1 over 0 has the positive and negative components of it, but what makes sense here is the positive infinity. So, which means, obviously, if you look at the graph, the rectangular hyperbola If you look at the rectangular hyperbola, you're able to realize, therefore, that this rectangular hyperbola, if you look at a simple function like f of x, right, f of x being 1 over x, okay? So if you look at f of x being 1 over x, but x positive, you're going to have this. But now when we are closer to the origin here, getting closer to the origin, you can see the function approaches, the 1 over x function approaches infinity. It goes to infinity there. Okay, so we have that. The conclusion, therefore, is that hence f of z equals 1 over z is actually not bounded. Is not bounded since there is no constant m greater or equal to 0 such that the modulus of f of z is less or equal to m for all z in C. Just like that. Okay. Just like that. So the function is not bounded because it is actually a function that is strictly less than infinity there. So this is not bounded since there's no constant such that is the case. For all z in C such that the modulus of z is strictly bigger than 0. So that function there is not bounded. Okay. Now we focus on the next question. We look at question 5. Question 5, we need to show that z squared plus 1 divided by z squared minus 3z plus 2 is continuous for all z outside, right, outside the modulus of z equals 2. We look at the solution now to this. What is the solution to this? Right, a couple of things to consider here. So we let f of z be z squared plus 1 divided by z squared minus 3z plus 2. Right, for all z outside modulus of z equal to 2. Okay. Like that. Okay, now we need to consider a z0 that is in the outside that region. Right. Z0 outside that region. Consider an arbitrary right. If you consider an arbitrary Z0, consider an arbitrary Z0 outside this region. Thus, the first point, we take f of Z0 to be Z0 squared plus 1. We divide it by Z squared minus 3Z plus 2 is defined. It is defined with Z squared minus 3Z plus 2 being not equal to 0 outside modulus of Z equals 2. Okay. Note that Z squared minus 3Z plus 2 equal to 0 means therefore that Z minus 2, Z minus 1 equals 0. Z equals 2. Each of these things, Z equals 1 or Z equals 2, they actually, Z equals 1 is inside and Z equals 2 is, so we just comment on that. For example, for Z equals 1, the modulus of Z is the modulus of 1, which is 1 less than 2, so that Z equals 1 is outside. Is outside modulus of Z equals 2. For Z equals 2, we take the modulus, which equals 2, so that Z equal 2 is outside, well, is on the boundary, is on the boundary, is on the boundary of this circle here, of center 0 and radius 2 units. And the conclusion that we draw from this is that clearly the 1 and 2 are, this 2 is on the boundary and the 1 is inside, so that if you consider the region outside this circle, surely this is defined henceforth. F of Z equals this, is defined yes, is defined for all Z outside the circle of radius 2 units. Okay, now the next thing is to evaluate the limit. The limit as z approaches z0 of f of 0. So this is z squared plus 1 divided by z squared. Let me clean this up. Right, so here we then say z squared minus 3z plus 2. Z0 squared plus 1 divided by z0 squared minus 3z0 plus 2. Right, I mean, we note therefore that this here, this limit exists for all z outside, for all z k. Outside modulus of z equals 2. Now the third point, is to consider the limit, is to say the limit as z approaches z0 of f of z. This limit is f of z0, like this. This limit is f of z0. Hence, f of z0 equals z squared plus 1. Okay. You just clean this up. Which is z squared minus 3z. Hence, this is continuous. For all z outside the modulus of z equals 2. Okay. Now, we can make a remark here. What is the remark? Comment. Just a comment. So is to consider this. Is to consider this Argand diagram. Which is the real part of that. You draw a circle like this of radius 2 units. And now, if we are to look at the region outside, because we are actually looking at the fact that this is continuous for all z outside this. So we saw therefore that z equals 1 was inside z equals 1 because we have that the denominator was effectively 0 at 2 points. At 2 points and z squared minus 3z. In this case, is z minus 2, z minus 1. Or z equals 1. So we could see therefore that z equals 2 is like here and z equals 1 is there. Okay, so we can see z equals 1 is inside and the other one is on the boundary. So looking at the region outside this, you really can see that indeed the function is the limit exists, so the function is defined, and therefore it is therefore continuous there. Okay. Because there are 2 points of discontinuity. There are 2 points. 2 points of discontinuity. What are the points of discontinuity? Z equals 1 or Z equals 2. Those are the points of discontinuity. All right. Z equals 1 or Z equals 2 are the points of discontinuity of this function. The points of discontinuity, 2 points of discontinuity of f. So that is what we get. All right. And yeah, we have shown that the function is continuous for all z outside modulus of z equals 2, which is the circle. And which was the question. But to show that this is continuous for all z outside, and we've shown that. And so we're done. So yeah, so thanks everybody. Goodbye to you.